Let's do an example where we calculate the pH of an acid. And let's start off with a strong acid, like hydrochloric acid. Hydrochloric acid completely ionizes in solution. So when this breaks apart in the solution, all of the HCl becomes H plus and Cl minus in solution. So the concentration of H plus in the solution is 0.3 because there's one H for every HCl. So if we want to calculate the concentration or the pH of this, then we'll just simply take the negative log of our strong acid's concentration. And that will equal 0.52. That's a fairly low pH, but remember, this is a strong acid. Strong acids tend to have very low pHs. And it is also possible to have a negative pH if we have a strong enough acid. But in this case, it's a little bit on the lower concentration side. Even so, since it is a strong acid, they tend to have very low pHs. Now you'll notice that I wrote two significant figures, or two decimal places, in my pH calculation here. Now there's a reason for that. It turns out that in general, a pH probe, or some way that we can measure pH, is really only accurate to about 2 decimal places. So it is safe to generally just put 2 decimal places for your pH answers. That was a very straightforward calculation. Now, let's see what happens when we choose a weak acid, such as acetic acid. We'll use the same concentration, 0.3, but now we have a weak acid. Acetic acid. And we have 0.3 molar of this. Now, acetic acid, unlike hydrochloric acid, is a weak acid. And so not all of this proton will come off in solution. Only part of it will. And so we're going to need to do an equilibrium-based calculation to find out how much of this proton comes off in the solution. And for that, we'll need to write the Ka expression, or reaction, which is just acetic acid, this is aqueous, reacting with water, that's liquid, and that will be in equilibrium with its conjugate base, acetate ion, and that's aqueous, and H3O plus, hydronium ion, and that's aqueous as well. So there's our Ka reaction, and now we'll need to finish putting in our the rest of our ice table or rice table, whichever you want to call it. So we have our initial condition right here. It's 0.3 molar for our acetic acid. We won't care about the water because it doesn't go in the equilibrium expression since it is the solvent. And let's assume that we didn't have any acetate ions or an appreciable amount of H plus in the solution when we started. So we'll just put down zeros for those. Our change is going to be minus x. Again, not a factor here. Plus x for under acetate and plus x under H3O plus. Adding those up to get our equilibrium concentrations, we get 0.3 minus x, x, and x. Now we'll need to plug these numbers into our Ka expression, our equilibrium expression. This is the Ka reaction. The K for it will be in a table under Ka's for acetic acid. And if we look that up, the Ka for acetic acid is 1.76 times 10 to the minus 5. Let's write the expression first, and then we'll start solving the problem. So we have the acetate ion right here. And then H plus divided by our acetic acid concentration there. And again, we don't include water because that is the solvent. And solvents don't go in equilibrium expressions. So this is equal to, as I said before, 1.76 times 10 to the minus 5. You'll look these values up in a table, or they'd be given to you. And then let's substitute in our equilibrium concentrations. We know that the acetate concentration is our unknown X. Same thing for our H3O plus. And then our acetic acid is 0.3 minus however much turns into these. So let's put that in. Now, you'll notice that this is a quadratic equation, and we would need to use the quadratic formula to solve this. But there's a little trick that we can do in some cases, and this is one of those cases where it's probably okay. This minus x right here is really only important if a lot of the acetic acid dissociates into these two components. If only a little bit does, then this 0.3 number won't change very much, and we could ignore the minus x here. Now, there's a little rule for when you can do that. If the concentration of our acid or base, because this works also when we're doing bases, is 4 orders of magnitude bigger than the K, then it is safe to ignore the minus x. What is an order of magnitude? That's a power of 10. This is indeed 4 orders of magnitude different. This is 10 to the minus 1. That's 10 to the minus 5. Those are 4 powers of 10 apart from each other. So we could simplify this problem by just ignoring the minus x. Now, this problem is just 1.76 times 10 to the minus 5 equals x squared over 0.3. We'll multiply the 0.3 over to the other side, and then take the square root of that resulting piece, and we should get x is equal to 0.0023. Now, we look at this and we say, what does that mean? Well, first we can ask ourselves if the minus x part was significant. And 0.3 minus 0.002 is not that much different than just leaving it as 0.3. And so that assumption was probably okay. Then we can see here that X is actually the concentration of our acetate ion, but more importantly, it's also the concentration of our H3O plus. That is the concentration that we really want to know to be able to put in our pH expression, negative log of this concentration. That will calculate the pH. So pH equals negative log of this number. Which will compute to 2.64. And again, I generally just include 2 decimal places whenever I do a pH calculation, whether this is 0.52, 2.64, or 11.86. Doesn't matter, just usually include 2 decimal places and you're okay on significant figures. So that's an example of how to calculate for acids.